All right, so let's continue with the lecture here. This is still technically, well, as long as I can see. Okay, now it's moving. Okay, so let's continue with the lecture here. This is still technically lecture 1 for the Met Bio class. The Met Bio class only meets once a week, as you know, and as a result, we do at least 2 lectures per time. Basically, what this means is that we're going to sort of slide in and out of topics sometimes during the lecture. So if it seems like it's sort of set up to be, one module and then another module, it's because it is. But here we go. This is basic chemistry for Biology 105. In this class, you're only going to be required to know the very basics of chemistry, just enough that we can understand what's happening at the chemical level as we understand our chemical reactions in biological organisms. If you haven't reviewed this carefully, just read the textbook chapter on basic chemistry. It'll give you enough information for this class. Okay, to start, everything in the universe is made up of matter, with the exception of antimatter. But so everything that we know that takes up space and has mass, all of the stuff that we're going to be studying is made of matter. Matter itself is composed of atoms, and some atoms Okay, so here we're going to start the lecture. We're going to talk here about basic chemistry. So this is not going to be advanced chemistry. You don't need to have taken a chemistry class, except for maybe a high school one, to understand this stuff. But if you are lost or if you need a review, just take a look at the textbook. You'll get enough information from that and from this lecture. Okay, so matter is anything that takes up space and has mass. It's all of the stuff in the universe. Now, there are some exceptions to this, antimatter, dark matter, etc. But for our purposes, everything that we are going to be studying is made of matter. And that is composed of atoms. So atoms compose matter. And atoms themselves, when they are studied individually, are elements. So elements are these substances that contain only one type of atom. These copper shavings on the left-hand side are composed of elemental copper. They're composed of only the atom copper and nothing else. Just like it on the right-hand side is lead, which is composed only of the element lead. Atoms can form bonds with each other, which create molecules that have different characteristics than just the atoms on their own. So if you combine carbon and oxygen, in fact, carbon and 2 oxygen atoms, you get the molecule CO2. Okay, the human body is composed of a variety of different elements. And therefore a variety of different atoms. The critical 4 elements of life are carbon, oxygen, hydrogen, and nitrogen. And in the human body, 65% of the body is composed of oxygen. Another 9% or 9.5% is composed of hydrogen. And between those two, about 18% is composed of carbon. Most of these, oxygen and hydrogen, are in water. Whereas most carbon is contained in sugars and proteins. Okay, so oxygen, carbon, hydrogen, and nitrogen compose about 95% of the mass of living organisms when you take them together. Water, as I say, accounts for most of the hydrogen and oxygen. Carbon is the backbone of all biological molecules, including sugars and fats and proteins. And nitrogen is also found in the proteins. The mineral elements correspond to less than 1% of the body's mass, and then trace elements compose less than 0.01% of the body's mass. However, all of these are important for the functioning of the human body. Okay, so what is an atom? Well, an atom is composed itself of subatomic particles. These are protons, which have a positive charge, neutrons, which have no charge whatsoever, and electrons, which have a negative charge. The protons and the neutrons are found in the nucleus here in the center of this blue image. So these red ones with the plus signs are the protons, and the white ones with no sign at all are the neutrons. And then out in these orbitals around the nucleus, we find the electrons. Electrons are much smaller than protons or neutrons, have a much lower mass, and as I say, are found in these orbitals, these sort of clouds that surround the nucleus. The number of protons that are found in the nucleus of an atom determines what element it is. So if you have, for example, helium, you have this number 2 at the top, and that helium number is its number of protons. However, you'll notice that helium has a weight of 4. That means that it has 2 neutrons in addition to its 2 protons. Okay, so hydrogen, as a different example, has only 1 proton and a single electron. So the difference between helium and hydrogen is that 1 proton, but helium can also have neutrons. An atom contains an equal number of protons and electrons. That means that its electrical charge is 0. So if you're looking at a hydrogen atom or a helium atom, the number of protons and neutrons should be the same. If atoms gain or lose their electrons, they are then called ions. So if you see a helium ion, it would have 2 protons and maybe only 1 electron, and then it would have a positive charge of 1. Hydrogen can also lose its electron, so if it loses its electron, then it has a positive charge of 1 and retains just the 1 proton. Okay, so how do you form a molecule? Well, you form a molecule when you bind 2 atoms together. We express molecules by their molecular formula. So we have the chemical symbols, so the element symbols, and the number of those atoms that are present in the molecule. So on the right-hand side here, we have C6H12O6, which happens to code for glucose. And in this molecule, we have 6 carbons, 12 hydrogens, and 6 oxygens. A compound is any molecule that's composed of 2 or more elements. So nitrogen gas, N2, would be a molecule, but not a compound. It is correct to refer to C6H12O6 as a molecule, but it is a sort of slightly more specific to refer to it as a compound. Okay, so how do you form these chemical bonds? Well, you form them using the electrons. As I mentioned a minute ago, electrons orbit the nucleus in an atom, in this sort of like a cloud of probability. They could be in any one of these places at any given time, but we don't know exactly where they are. We just know that they're sort of there. You can imagine this sort of like you're looking at a racetrack, but all the cars are invisible. You know roughly where the cars will be. They'll definitely be on the track, but you don't know for sure where on the track they are. That's the sort of equivalent of the orbitals in this case. So these orbitals are arranged into electron shells, we call them, where each shell can hold a certain number of electrons. So the more electrons an atom has, the more of these shells are occupied. This is like a little bit outside of the scope of the class. You don't truly have to understand this, but just to show you what these shells look like, they can hold different amounts of electrons. So the first shell can hold up to 2 electrons, and the second and third can each hold up to 8 electrons total. So if you have an element or an atom with 3 electrons, the first shell would be filled, and then the second shell would have 1 electron in it. That would be the case of lithium here, right here. Whereas hydrogen, which only has one electron, is only occupying the first shell of its orbits. So here is an example of nitrogen. In nitrogen, we have this nucleus with, with 7 protons in it. And then surrounding those 7 protons are 2 different electron shells. The first one here has 2 electrons in it, and then the second one has 1, 2, 3, 4, 5, for a total of 7 electrons, which cancel out the charge of the 7 protons. So what does this have to do with chemical bonds? Well, for atoms to form bonds with one another, the goal is usually to fill the outer shell, which you'll remember can hold 8 electrons. The exception to this is hydrogen, which is only filling its very first shell. So if you take 2 hydrogen atoms, they each have 1 electron, they can share those 2 electrons and therefore fill their electron shells. So if you imagine a hydrogen atom has 1 electron, and it wants to share, or it wants to fill that electron shell, but if it fills it with another electron, then it will have a negative charge. So to satisfy this, to fill that shell without adding a negative charge, 2 hydrogen atoms interact, and in the middle, they share those 2 electrons. Let's see. So what happens in the case of something more complex, like sodium and chloride interacting, is that so when they share the electrons, they do this chemical bonding, but they can share the electrons in different ways. So one way to do that is for one of the atoms to give its electron to the other. And what occurs when that happens is you get 1 positive ion and 1 negative ion, but you'll see that both of them have their electron shells completely filled. Sodium has its second electron shell with 8 electrons in it, and chlorine has its third electron shell with 8 electrons in it. This is favorable because now both of them have full electron shells, but they both have a charge. This molecule that's formed is called sodium chloride. So ionic compounds are usually referred to as salts, and in this case, sodium chloride is what we would call table salt, just regular salt, culinary salt that you have in your kitchen. Another way of doing this is to form a covalent bond. In covalent bonding, rather than taking an electron from one and giving it to the other, the two atoms share their electrons. So here we have fluorine and hydrogen. Hydrogen has only 1 electron in its outer shell. It wants to have 2. Fluorine has 7 and wants to have 8. And so they share. Now they both have full outer electron shells, fluorine with 8 and hydrogen with 2. And there is no change in charge because they're sharing the electrons. Most biological molecules are held together by covalent bonds. So these are bonds of sharing, where the electrons are shared between the two. So if you think about the way that these common atoms need to fill their electron shells, oxygen needs 2 electrons, nitrogen needs 3, and carbon needs 4, we can understand why a molecule, for example, like H2O, is energetically favorable and why that's its formula. Oxygen needs 2 electrons to complete its electron shell, and hydrogen needs 1. And so between these two, you need 1 oxygen and 2 hydrogens to stabilize the outer shell. And that results in H2O being the molecule that we create. Now, it is possible to create other molecules, but these would be very energetically unfavorable and are not common whatsoever. Carbon is a really key atom in our biology specifically because it forms 4 covalent bonds, which lets it create very complicated molecules. Okay, so how do we form or break these bonds? Well, through chemical reactions. A chemical reaction has reactants, that is the molecules that we start with, and also products, that is the molecules that we end with. So if we take the reactants of 2 hydrogen gas molecules and 1 oxygen gas molecule, and we go through the reaction, we produce 2 water molecules. Chemical reactions can both make and break bonds, and they can be a little bit more complicated than that water reaction we saw just a little bit ago. This ethanoic acid and this methanol can combine to perform methyl-ethanoate and water. And what's happening there is that water is being removed from the 2 different compounds as they're being combined to produce 1 compound and water. Most of these biological reactions are reversible. That means that they can occur in both directions. The direction that the reaction actually goes will be determined by the amount of the reactant and the products present, and which direction the reaction is most energetically favorable in going. So for example, you can combust methane, you can burn natural gases, and this produces carbon dioxide and water. You can also produce methane and oxygen from carbon dioxide and water. It's just much more difficult to do. So you can go this way by producing heat, carbon dioxide, and water. That's burning gas. But you can also go this way by capturing carbon. So actually, there should be 2 arrows here. There should be 1 arrow leading one way and another arrow leading the other. You can put the water back and break that bond again to produce ethanoic acid and methanol. Okay, so one thing that you should know about bonds and the bonds formed by chemical reactions is that they are not always equal. So oxygen has all of these electrons, and it has a space for 2 more in its outer shell. But some atoms, like oxygen, they attract electrons more strongly than others. So oxygen is actually quite a lot stronger at attracting electrons than hydrogen atoms are. We call this feature electronegativity. So oxygen atoms are much better, much more electronegative than hydrogen ions are, or hydrogen atoms are. So oxygen atoms are better at attracting electrons than hydrogen atoms, and we call them more electronegative. What this results in is an uneven sharing of the electrons in the molecule. And what that results in is a molecule that has a polarity. It has a more negative side, an area where the electrons hang out more often. And it has a more positive side where the electrons hang out less often. If this sounds to you a little bit like a magnet, that's correct. This forms a polarity in the molecule, one side that is different than the other side. What this means is that you can take 2 different molecules and they will be attracted to different parts of each other. The oxygen atom, being more negative, is going to be attracted to the more positive hydrogen atom on the other molecule. And this results in a very weak bond that we call a hydrogen bond. Hydrogen bonds are weak on their own. They break and reform very regularly. But when you have them in aggregate, when you have lots of hydrogen bonds, what happens is they resist change. And you can get things like water striders, like the bugs walking on water, or lizards that can run across water. So again, I want to reiterate, individually, hydrogen bonding is very weak. The bonds can break very easily in these molecules, but collectively, they can be strong. They can hold DNA strands together. They help proteins to hold their shape, and they can even support the weight of animals. The key to this is that they form large lattices. So individual atoms will bond with one another across a large space, and this forms this sort of lattice work of bonds that are individually weak, but together, when you add them all up, are strong. But it's important to note that not all biologically important molecules are polar. In fact, some molecules, like fats and lipids, are made up almost entirely of atoms with similar electronegativities, like carbon and hydrogen. What this means is really long lipids, like the one you're seeing on the board, are not polar at all. In fact, we would call them non-polar. Okay, so to review, the three important bonds for biologists are ionic bonds, which have a medium strength and are atoms that are bonded together with opposite charges, where one atom donates its electron to the other. The covalent bond, which is the strongest, where the joined atoms share one pair of valence electrons, or sometimes more, and these can be polar or nonpolar bonds. And hydrogen bonds, where they have a weak bonding strength, but can be strong in aggregate. Okay, so what does this mean? Well, in animals and in biology in general, water is a really, really important compound, a really important molecule. And it's so important, in fact, that we have lots and lots of water in our bodies. Inside of our cells, in aggregate, if you added up all of the cells in our body, you have about 25 liters of water. In the fluid between the cells and your blood, there's about 12 liters of water total in your body. And in your blood plasma, there's about 3 liters of water total. So that's quite a lot of water. Water acts as a solution. It dissolves everything inside of your body. And it does this because it's polar. So this polarity helps it to do what it needs to do. What polar molecules allow your body to do is to dissolve things in water. These molecules we would call hydrophilic. So hydrophilic molecules interact with water and dissolve in it, and water dissolves them. Molecules with ionic or polar covalent bonds are the ones that are hydrophilic. And this is because they want to be attracted either to a positive or to a negative pole. So if they have positive and negative components, like ionic bonded molecules do, or if they themselves have polar covalent bonds, they can more readily interact with something that's polar. Like attracts like in biology as well. So we just said that water can dissolve things, but what does that really mean? What does it mean for water to dissolve things? Well, it means that the water molecules are surrounding the atoms of, for example, an ionic bonded solution and sort of holding on to those atoms. So here we see a man who's eating a plate of French fries with salt on them, and the solid NaCl, the solid sodium chloride crystals, are found, they find their way into his stomach. In the stomach, the water that's in the stomach acid gets attracted to the positive and negative atoms in the sodium chloride and sort of disassociate them into the water. What happens here is the ionic bonds break when they dissolve, but covalent bonds don't do the same. So the ionic bond between sodium and chloride breaks, and a new bond, a hydrogen bond, is formed between the oxygen molecules of the water and the sodium that is floating around, or the hydrogen molecules of the water and the chlorine. So we have hydrophilic things that can dissolve in water, but we also have hydrophobic things, that is, things that don't dissolve in water. Non-polar molecules like hydrocarbons, oils, fats, lipids in general do not dissolve in water. And you're probably familiar with this, right? When you make a vinaigrette, you combine oil and vinegar and you shake it up, it doesn't actually combine. And if you leave it alone after a while, it will re-separate, just like this glass of oil and water on the right-hand side. This is because the oil can't dissolve in water because it's non-polar. It's not the same as the water is because the water is polar, and so the two don't interact well. What actually happens when you put oil in water is kind of cool. This is an example of a molecule that has two different regions on it. So this is a specific type of molecule called an amphipathic molecule. It's neither polar nor nonpolar. It has a polar end and it has a nonpolar end. So the polar end here is represented by the blue circles, and the nonpolar end is represented by the white strands. And what will happen is if you add amphipathic molecules to water or to some polar substance, they will face so that all of their polar regions are facing out and all of their non-polar regions are facing in. This is the most energetically favorable because the polar hydrophilic areas get to interact with the water and the non-polar, non-hydrophilic, in fact hydrophobic areas get to interact with each other. And this forms a structure called a micelle. A micelle is a circular sort of ball-shaped structure that allows this energetically favorable arrangement of amphipathic molecules. This, incidentally, is how soap works. Soap is an amphipathic molecule. It has a hydrophilic head that allows it to interact with the water, and it has hydrophobic tails that allow it to interact with grease or oils on your hands. So when you wash your hands, the grease interacts with the hydrophobic tails, and the hydrophilic heads interact with the water and allows it to be washed away. So that's how soap works. And so this covers the biological molecule types and the introduction to chemistry that we're going to cover in this class. We will also talk a little bit about biological molecules, etc. But this is what you need to know, that molecules form bonds, ionic, covalent, or hydrogen bonds, and that these resulting molecules can be hydrophilic, hydrophobic, or amphipathic. And this covers the sort of like introductory chemistry module. We'll talk about more as we go, but this is the end of this lecture. So thanks for listening, and I will see you in class.